Okay, we are going to talk electrolysis today. Electrolysis. And then electroplating beyond that, which is just a little bit different form. Okay? All right. So, galvanic cells. Let's do a quick little, whoa, that is not how you spell it. Quick little comparison. Galvanic cells, electrolytic. What's true about galvanic? What's an E value look like? Positive, he says. And because of that, delta G is, or at the same time, delta G is negative. It's a spontaneous reaction. Spontaneous. Electrons flow from most likely oxidized to most likely reduced based on our potentials. Reduced. Because reduction potentials tells us, boy, that doesn't look good at all. Our reduction potentials tell us how much elements or things want electrons, or compounds like electrons. And the electrons will flow away from the things being oxidized because losing electrons and going to things being reduced. Electrolytic cells are the opposite. Rather than us getting energy from it, we're putting energy into it to try to reverse the flow of electrons. This is what happens every night when you plug in your phone. You are reversing the flow of electrons by putting energy into it. All right? So, whoa, that is awesome. So the difference, delta E is, E is negative value. Delta G is positive. It's not spontaneous. We have to put energy into it to make it happen. And the electron flow, opposite, let's keep it simpler, opposite galvanic cell. And I'll show you what I mean by that. Here's a pretty picture about this with copper and zinc in your book. That is nice to look at. But we're going to do examples that we can actually show, well, I can show demos of doing that too, and the electrolysis, but the demos that we'll show with this is astounding and amazing at the same time. Not easy. So what you have to do is hook up a battery of some sort. How much voltage does that battery need to be? We'll talk about that. That's where we're headed. So let's say we have K, that's potassium iodide I'm using here, right? Yeah. Ki, oh, and it's a liquid. It's not aqueous, it's a liquid. We'll do aqueous next. Don't worry, don't fret. It's going to be okay. And I'm going to put electrodes in there. And I'm going to have a little battery source. Where one side is positive and one side is negative. That's a battery. And I'm going to hook up wires to these little electrodes. And in here, I've got what? I've got some potassium ions and I've got some iodide ions. I got ions. So, what's going to happen? If this is molten, this is what I'm talking about here, liquid potassium iodide, molten potassium iodide. All right? What is going to happen to this electrode? Is it going to have a negative charge or a positive charge, do you think? Since we have a negative part of the battery here, it's going to push electrons onto it. So we're going to have a negative charged electrode. Electrons are going to be pulled from here, so this is going to be a positively charged electrode. So we're going to have some extra electrons here that were pushed onto here. Which one of these ions is going to be attracted to that negative electrode? Potassium. They're going to go there. And the potassium plus one electron, so what's going to happen is going to make potassium, metal. I didn't give myself much space. Shoot. Just for sake of space here, we'll move it over, make it a little smaller, move it over. K plus one electron yield K. Alright? The reason is because I need to put a voltage there. The iodine is negative, will be attracted to this. We'll lose an electron to it, and what do you think it's going to form? Iodine. And I'm just going to balance it right away. Electron. Let's figure this out. If I look on my green sheet, what is my potential of potassium, the reduction potential of potassium? Because it's gaining an electron here on top. What do you got? Negative 2.92. Ugh, that's getting ugly. But that's volts. Put that there. How about iodine? 0.53. Is that the reduction potential? Okay, we flipped it though, right? Iodine's being oxidized. So negative point, did you say 5.3? 5.3. It's going to take that many volts to make this happen. Okay? I have to add those up. What do I get? Minus 3.45. Think about my math here. Okay? That's the number of volts needed here. At least 3.545 volts needed to run. That's the number of volts that would be needed. So if I had a AA battery, it wouldn't work. It's only 1.5 volts. That's what AA batteries are. If I had one of these fancy little 9 volts, like these guys, sure, it would work. I have plenty of voltage to make it happen. Rachel, it's okay. You didn't mean it. So, you would need that much to make it happen. Questions so far? That's kind of weird, but we're pushing the electrons the other way. Now, what is this side here? Is the potassium the cathode or anode? Oh, it's tough, isn't it? Still the same thing holds true. Where reduction takes place is the cathode. Where oxidation takes place is the anode. What's taking place here? Reduction. This is still the cathode. And this is still the anode. The electrons are still flowing this way. But compared to a regular galvanic cell, if you compare two of the same exact, like iron and copper next to, or zinc and copper next to each other, the electrons would flow the opposite way compared to this. We're pushing electrons in where they would typically be leaving. All right, let's go a different situation. Let's make it fun. Well, it's always fun. Let's make it Ki aqueous. I'm going to move over so I have room to put things. So what's in the solution now? I don't like what I did there. Water and the Ki. Same setup, but now we have water in here, K plus in here, I minus in here. Same setup, battery, negative, positive. So, we have different situations. And you might say, this would be awesome. I've got this Ki. I've got this in solution right now. We're going to make potassium metal and water. This is going to be crazy and explosive and amazing all at the same time. Unfortunately, it's not going to happen that way. Let's talk about why. Okay, let's talk about the reduction part of this. Reduction. With the last one, what was being reduced? The potassium or the iodine? Potassium. Okay. And if the potassium is reduced, come on, buddy, it is K plus 1 electron yields K. And my potential there is, I can't remember, negative what? 2.92 volts. All right? However, we have other things in here that might like electrons. We have water molecules that might like electrons. Look at your sheet. See anything with water plus electrons on your sheet? How many H2Os? 2 H2O plus what? 2 electrons yields what? H2, so a gas plus 2 OH minus. And what's that potential? Negative 0.83. Which one's going to happen? The water. Okay? What this means is that the water is more likely to gain the electrons than the potassium is. So this is the one that's going to happen. And we'll run this one in a little bit here. But this is the one that's going to happen because it is more likely to be reduced. So the water being involved here is a little issue. All right? What about the oxidation side of things? Oxidation. In the last one, we said that iodine, 2 of them, lost 2 electrons to become I2. What's the voltage when we flipped it? Can't remember. Negative 0.53. All right, what about water? One thing to notice here, look at your sheet. Okay? We need water to be on the left-hand side of this equation. And we need electrons to be on the right-hand side of the equation for it to be an oxidation. Yeah? I can't flip this equation here and make it oxidation. You see that? If I flip this equation, the electrons are on the right, but so is my water molecule. I've got to have water losing electrons. Do you see another equation that's like that we can flip? Where there's water on one side and electrons on the other. Way at the top? Okay? So flip it for me, Trevor, and read it to me. Oh, then I missed the other thing. For 2OH? O2. Thank you. And what's the voltage of that if you flip it, Trevor? Negative 1.23? Super. Okay? So water also wants to lose electrons, and so does iodine. Which one wants to lose them more? The same rules apply number-wise. The iodine ions or the water? Same rule applies. What I mean by that is the higher number means more oxidation possibility. Okay? So the iodine has a higher number. They're both flipped, but this means, and if you look at your sheet, there's another way to look at your sheet, folks. Your sheet was organized as a reduction potential, with the things at the top most likely to be reduced. So the very, very most likely thing to be reduced on your sheet is what? Fluorine or fluoride ions? Which one? What's gaining the electrons, the fluorine or the fluoride ions? Fluorine, right? F2 is the most likely to be reduced. What is the least likely to be reduced on your sheet? lithium ions. All right? We could easily take this sheet, write the equations flipped around, and flip the whole thing, and now the bottom right thing is the most likely to be oxidized, lithium. And the next most likely thing to be oxidized would be cesium, then potassium. And if you have that, you have yourself an activity series of metals. Like you look there. That'd be the order that they'd be going in. Most likely to be oxidized, bottom right. Most likely to be reduced, top left. So we could flip it and have the most likely to be oxidized. So in this case, the iodide ions are more likely to lose electrons, more likely to be oxidized than water is. If I want to add all these up, I've got 2 electrons on both sides. Let's just look at our balanced total situation. I have 2 waters plus 2 iodides yields H2 plus I'm losing track of everything. Plus our other things over here. What do we got? Oh yeah, I'm looking at the wrong things. Sorry, I2. Only the ones here. 2 OHs, that perfectly. And then this I screwed up. Oh no, I didn't. Did I? I didn't. Is this right? Sorry. If you're listening to this on Schoology, I'm sorry for just yelling. What is my total voltage needed to make this happen? What's the total voltage needed to make this happen? 1.36 would be needed. Let's talk about evidence. At the negative electrode, what's going to happen? So this negative electrode gaining electrons, I should have a gas. So coming off of this, I should have H2 and OH minus. I'm looking for evidence of this reaction. On this one, I should have I2. Now, if I was really technologically savvy, I would now say, well, let's look at the demo and put it on Schoology. But you have to be in class to see this one this time. Oh,